Hi, so in this video we are going to build an ARIMA model using R. So we'll take the dataset that is there in the folder. So the dataset stock price data and stock return data. So it's a financial market dataset. Okay, and the name of the dataset is Nifty. So which is because it's taken from the National Stock Exchange, and we're taking the Nifty index values and the corresponding return, and we'll see how they're different and how forecasting these two different variables is different and why it is different and so on. The first thing that we'll do is just let's first import it. So we'll just read it first, and then uh, let's print a few observations. Okay, so when we print few observations, what we see here is date. It's a daily data. It starts with 1st of Jan 2003, and then we have got the prices, and then we have got the returns. Prices of the stock index and the return on the stock index on that particular day. Okay, on 1st of Jan, prices of a particular index and then returns on that index. Return is calculated as log of the price of today divided by the price of yesterday. Okay, so this is the log return. Okay, and in finance, people are more interested in returns than prices. That's why return is an important variable in finance, and forecasting return is what is an important thing. There is another important aspect to return also, which we'll see in this particular video. Alright, so we'll talk about it later. So let's load a few packages that are important. Uh, the T series package is important. So we'll load the package T series. We'll also load package ggplot for plotting and all. Okay, so we'll attach the data to ensure that we don't have to specify the data name all the time. Okay, so let's explore the two variables which are in front of us. Okay, the prices and the returns. Okay, let's look at how prices look like. All right, so this is how the prices data look like. Okay, all right, you can see that there is an upward trend, right? It goes down initially and it goes up, it never comes down, right? This type of data is having an upward trend, and this seems to be a non-stationary data. A stationary data normally comes down to the mean, right? It will not be like this. It's stationary data mostly comes down and then goes up, comes down, and so on. That means it should have constant mean and constant variance. This particular data seems to have a constant variance or near to constant variance, but the mean is changing. That means if you look at the first 100 observation and take the mean, and the next 100 observation and take the mean, it is changing. It is going up and up and up. So it is increasing over time. So this seems to be having some sort of a non-stationarity, and that is an issue in time series forecasting. And for that, one has to take steps to make it stationary and then use the traditional forecasting model like ARIMA, ARMA in order to forecast. Alright, so let's look how returns look like. Okay, so when we look at returns, it's different. You can see the return data is surrounded, or it's spread across percentage 0. Sometimes there is a positive return, there is a negative return, and so on. And it seems to be having constant mean. The mean is centered around 0, and it seems to be having constant variance as well. There is slightly more variance across the end at the end of the series. Otherwise, you can see, except these few outliers, these few observations, you can see the constant mean and constant variance across this particular series. Okay, and that's why is it so? Why return is more likely to be stationary than the prices? Well, the prices can go up and go up and so on continuously. Okay, so that can have a trend, but return is just the difference of that, difference of your today's price minus yesterday price divided by that. So so there is some sort of a difference that we have taken, and in theory of ARIMA model we have learned that whenever we do a difference of a series or difference of a non-stationary series, we tend to be more stationary. Now whether this return series stationary we are not sure about it, but it looks stationary, or we are more closer to a stationary series. That's what it is. All right, so we'll first take the return series and do the forecasting model using ARIMA. Why so? Because the return series looks much simpler than the price. Because for price we have to do some sort of differencing, and then we'll take a decision on what order of differencing is required to make it stationary and so on. But the return series looks very stationary, so let's take that first, and we'll go to the price series later. All right, the first thing we'll do is um, the first step of ARIMA model. If you follow the box and Jenkins steps of doing an ARIMA model, first step is model identification, to see what is the order of the ARIMA model that is suitable for this particular data. Okay, so first we'll do the stationary check. Okay, let's do a stationary check. We are not sure whether this is stationary. We think that this is stationary, but we are not sure whether this is perfectly stationary. So let's do a decay Fuller or augmented decay Fuller test. Okay, so we're doing an augmented decay Fuller test on the return series, and then the alternative in the hypothesis is stationary. That means if alternative is there, then we are sure that it's stationary. So let's run this. All right, when we run this, we get the statistics value. So the p value is 0.01. That means we are rejecting the null hypothesis that it is non-stationary. So we are accepting the alternative hypothesis that it is stationary. Okay, the p-value is 0.01. So we are sure that it is stationary. All right, so no issue. So we don't have to differentiate, or we don't have to make it stationary. All right, so let's plot the ACF and PACF. Remember, what is ACF and what is PACF? Well, these are some functional form of the data which tells us the order of the AR terms and the MA terms in the that should be in the model. Okay, so let's plot the ACF first. All right, so the ACF, if you look at the ACF, you can see the only significant term in the ACF which is significant is the first one, right? Don't confuse with the this one, because this is again this is the correlation with the same one, which is always going to be 1. So it is only the first or first lag which is significant, right? This one, because this lies within the blue line. So anything that lies above the blue line is a significant. Others are on insignificance. So all insignificance for the lags, only the first lag is significant. So this shows an AR1 pattern, or AR1 is something that it indicates, and we'll also take that into consideration. Okay, let's run the PSA. Another good thing here to note here is that it is decreasing over time, and that's a sign of a stationary series. Uh, every stationary series, there is a fast decay, or there is a very what would I say, steeper decay of the the ACF value with lags. Okay, so it seems to be an AR1 process, and it's a stationary process, which it says. So let's plot the PSF. Okay, so when we do the PSF, we can see that uh, the only okay, so we can see the uh, first one is significant, and others are all insignificant. Okay, so there seems to be an AR process, and we'll also include a couple of MA terms which may complement the AR process. So that's what it says. We assure that we are not going to do any differential. So the middle term in the ARIMA, which is the Q, is going to be 0 all the time. Okay, that's what we are sure about. Okay, so there is evidence that we have AR1 and combination of maybe AR and MA process. Okay. The next step in the box Jenkins method of doing or building an ARIMA model is the model estimation. So we'll estimate the model and see which one is providing us the best fit. Okay, and you need not just try out the AR1 model. You can try a variation of that and see which one is the best. Okay, so let's run the first model, which is the AR1 model. So we'll use the procedure ARIMA returns, which is the return series, and then the order here is 100, right? So what is set? The first one is the AR term, middle one is the differentiating that we have done, and then the last one is the MA term. Remember, we are not doing any differencing here, and we are not using MA term in the first one. Okay, we'll include that later on. Okay, so let's run this. All right, when we run this, we have found that there is an AR term. So the AR term, the coefficient for AR term should not be closer to 1. That's one thing we need to check. Why so? Because the moment it is closer to 1, it indicates some sort of a random walk model, and that is a non-stationary model. But it is not that, so it is good, and it also very close to significant, right? The statistic that is important while selecting the best fit is the AIC, the Akaike information criteria. The lower the Akaike information criteria, the better is the model, right? Or that's how you choose a model. Let's try to include another AR term, and let's see what changes do we see. Alright, so when we include another AR term, we're seeing that the AIC value is increasing, and that's not a good thing, right? Because the least AIC is what is expected. That means adding an extra term, AR term, is not improving the model in any way. Okay. Okay. All right. So let's include an MA term. Okay. So in the place of moving average, we have just used the first order moving average along with the AR1. Okay. Okay. So this is ARIMA 101. So let us see. Okay, the MA term is not significant. Let's see whether it's all right. It's again the AIC value is more than the first one. The first one is minus 1514, which is the least among the three models that we have tried. So it is clear that the first model ARIMA 100 is the one which is fitting the data more than the other two models. That should be the ideal choice for us. Now, selecting the model is more like art than science, because sometimes you can try more models, and you'll be confused with the fact that sometimes the AIC value will be very close to each other, like very very close. And but in this case, it's pretty clear. You will come across cases where it is not that straightforward. Okay, and probably in the next section, when we do prediction for prices, we might face this issue of finding out the best fit where it is a non-stationary case. But in this case, it's a pretty stationary case, so it's seems to be simpler. Now we are going for ARIMA 100, right? That's the best fit we have found. The last step in the ARIMA forecasting is, okay, so before last step, what we can do is we can do some prediction. Okay, maybe we'll just do the last step and then do the prediction. That is better. Okay, now we have done the fitting. Let's do the diagnosis. Okay, now that we have, we know that this model is good, but how are we sure that it is fulfilling the statistical assumption in the ARIMA? The statistical assumption in ARIMA is that the error term or the residual terms should follow white noise. It should be a white noise, mean 0, standard deviation of 1, and no correlation, no pattern in the error term. It should be completely random. Okay, how do we test it? Let's test it out. There is no autocorrelation in the residuals. So how do we test it? We can use TS diag. Okay, and then okay, so we have to first predict and then we can do that. Okay, sorry about that. So we have to first predict. So how do we predict? We have finalize the model, so we can just use arima.final and then use the same ARIMA and then the series and then the model that we have finalized. Alright, and then we use the TS diag in order to diagnose the time series residuals. Okay, so let's run this. Alright, when you run this, you will get the standardized residuals. Okay, you can see that it is very random and there is no cluster of data. You can see there's no pattern, and it seems to be okay. Another important thing is that you can look at the ACF. Okay, ACF will tell you the autocorrelation, and you can see there is none of the autocorrelation function values for different lags is significant. That means the error term doesn't have a correlation or doesn't have a pattern in the residuals. All you can see is within this blue line, right? None of them is out. Don't confuse with the first one. It's always going to be 1, but rest are all between these two boundaries, right? The blue boundaries, right? Hence, we are sure that the model is fitting the data well and the statistical assumptions are all met. Alright, now that it is done, we can use this model for the prediction. Let's say we want to predict it for the next 10 periods. Okay, for the next 10 days. Remember, ARIMA model works well for the near future. It doesn't work well for long-term forecasting. So let's say we want to forecast for next 10 days, the return for the next 10 days. Okay, so what we can do is that we can use the function predicted, and then use function predict. Then arima.final is where we had saved, by using save the results from the function arima, and then use n.head equal to 10. That means we are going to predict the values of return for the next 10 periods. Okay, and then when you run this, you will have the predicted values in the predicted. So let's print what is there in the predicted variable. Alright, so when you look at here, you will see the predicted values of return, okay, for the next 10 periods. So these are the predicted values of returns for the next 10 periods. You can change it to 20 periods. Okay, let's see how it's coming. Okay. Alright, so it is going to give you a prediction for next uh, 4-5 period correctly, and then it's going to give a very weird prediction. But you can see the first few periods it's changing, and then that is seems to be constant, because as I have said, ARIMA model doesn't do good prediction for long term. It's only for the next few periods, which it is a is ideal or suitable way of uh, doing forecasting. Alright, so we in this particular video what we have learned is the different steps of building uh, an ARIMA model in R by using the box Jenkins method of doing forecasting. The first step, we identified which the order of the ARIMA. We first checked the stationarity, and then we found out which order of AR is what the data is following, and then we in the next step in the model estimation we included a couple of more ARIMA orders like ARIMA 2 0 0 ARIMA 1 0 0 1. You can have even more models like that, and then finalize the one which is best based on the parsimony, that is by looking at the AIC value. So the one with least AIC value is the best one, and then we diagonized the residuals by estimating the model, and then using the tsdiag command or keyword or the function, and then when we plot it, we found that the ACF of the residual terms is insignificant. In all the cases, it is coming under the boundaries, blue boundary, or the upper limit, the lower limit for significance. And then once we are sure that it is, it's the residual is white noise, we went ahead and predicted, and we have seen that ARIMA is providing good prediction for the near term, the near couple of periods in the future. Okay, so that's about ARIMA forecasting in R, and we have done it for the series return, which seems to be already a stationary series. Now we'll go to, in the next video we are going to see the same thing for prices, which is not a stationary case. It's a non-stationary model. It's a non-stationary data, and we may have to we will have to do make it stationary first, and then follow this follow the same procedure that we have, follow the same steps that we have followed in this case. See you in the next video. Hi. So this is the second part of the ARIMA forecasting using R video. In this particular video, we are going to take the second variable in our data, which is the prices. In the previous video, we learned how to we learned about forecasting the return, stock return. And in this particular video, we're going to learn forecasting the prices. And the reason why we had separate, we are doing it separately, because the behavior of stock price and the behavior of stock return is different. We have seen that the stock return tend to be more stationary, or tend to be more suitable for a simple time series, whereas stock prices tend to have an upward trend in our data. It could have a lower downward trend also sometimes, but in our data it's upward trend, and that seemed to be violating some of the basic assumption of stationarity, and it is clear that it is a non-stationary series. That is and that has to be dealt in a way to make it stationary, and then the standard procedure for ARIMA can be followed. So let's see. Okay, so we'll first load the time series packages, and then we'll attach the stock data, and then let's start with the exploration. So let's first see how the prices looks like. Okay, we have seen already there is an upward trend, and that seem to be non-stationary. We have to do a statistical test to prove that this is non-stationary, to be sure of it. So we'll do a accumulated decuplier test for the prices data, and let's see what the p-values. The p-value is 0.95. That means we're sure of this fact that it is non-stationary. That means we are accepting this null hypothesis that it is non-stationary, right? Okay, so if the data is non-stationary, what do you need to do? You need to do a differencing. And what should be the order of differencing? Well, that's a very interesting question. Start with the first differencing and then see if the data becomes stationary or not. If it is not, then go ahead with second differencing and so on, right? So we'll do the first differencing. Okay, so what do? We simply define a new variable, d dot prices. It's a new variable, and we take the difference. The function diff is going to do that for us. All right. So we have now a new series which is difference of prices. Okay, we can also do a summary statistic of it to just to know how these two things look like. Okay, d dot prices. Okay, so let's run this, and you will see prices has a mean of 1236, whereas when you do a differencing, the mean, median, minimum, maximum, everything is different. Okay, because we have done a differencing of the data, right? So it becomes little more stationary. Okay, so let's see whether it's stationary or not. So we'll do a decuplier test again. All right, so the p-value in this case is 0.01. That means we are rejecting null hypothesis, accepting the alternative hypothesis that it is stationary now. That means the first differencing itself is making the data stationary. We don't have to go to the next order of differencing. We don't have to differentiating it again, right? All right, so let's look at the ACF and PACF. Let's look at the ACF first. Okay, if you look at the ACF, only the first order lag is significant and the rest are all insignificant, because it all lies between the blue line, between the confidence interval, and hence it seems to be following an AR1 process, right? So let's look at the PACF. None of the lags are significant. Okay, but we'll include some of these MSC lags, and just to see whether it really improves or it doesn't improve. Okay, most probably it's not going to improve, because it seems to be none of these lags seem to be significant, or maybe the first lag is significant. Let's see that in a model estimation. So we go to the model estimation, the step 2 in the Box-Jenkins ARIMA model estimation. So remember in this case that we have taken the new series data. That means we have already taken the differencing data. So don't change the differencing operator as 1, because we have already taken the differencing. So you don't have to do that. Just keep it 0. If you make it 1, that means you are differentiating again. So you are doing twice differentiation. Now if you use only prices, then you can use here 1. But since we are using the variable which is already difference, you don't have to use. That means we are already using it as a differentiation. Okay, so let's run this, or let's do the estimation, and you can see the AR1 term, there's only one term. So remember the first remember this is a ARIMA 111 model. Okay, so the first model is ARIMA 110. Okay, and the AIC value is 2142.5. Okay, let's go to the next one. So the next one is ARIMA 210. Okay, so we are taking two AR term in this case. So the two AR terms, you can see that the AIC value is increasing. That means it's not adding any value to the model. So no point in adding another AR term. So let's see whether MA terms really makes a difference. So now we are having ARIMA 111. Okay, one AR term, first difference, and first one MA term. Okay, so this one is ARIMA 111. Remember, this is 0, but we are using the first difference of variable, hence it means that it's the first difference is there, so it's ARIMA 111. Okay, alright, so let's estimate it. Alright, so it's very close to the first one, right? 2152, so AIC value is very close. That means it's also a suitable model, right? You can use either of 110 or 111. Okay, both are fine, right? So let's go with 111 because we have an MA term, and it seems that the results are going to be more stable with an MA term in place. But the AR ARIMA 110 is also doing fine. Okay, this can be further validated by using a cross validation technique. Okay, so some people take a sample of the data, and then if you're confused, like I was saying in the previous video, sometime it is not going to be very clear which one is the best model. Some of the model could be exactly same AIC value. That should not be the criteria alone. One should actually go ahead and check the cross validate it and see if there is a significant difference between these two orders, and then you can decide which one is more suitable. We can go ahead with ARIMA 111. Okay, so we'll do the diagnosis of the residual terms. Okay, so we'll first estimate it and then do the diagnosis. All right, now when we do the diagnosis, we see that there is no clustering of the residual data points. There is no pattern, and it seems that it is revolving around 0. So it's very similar to a white noise process. And we can also see that none of the autocorrelation function with respect to the lag is significant. That means everything is under this confidence interval, the blue lines, right? So there is no autocorrelation between the residuals. Hence, there seems to be the model seems to be statistically fitting the data, and there is no violation of the assumption of ARIMA model. Alright, so that's the third step, or the last step of the ARIMA model forecasting. Okay, so step 3. Alright, the moment it's done, you can use this model, a final model for forecasting, like the way we did last time. So we just have to use the estimate it and then predict it and then find the values. So we can use the function predict in order to do that. Okay, and we are going to predict the next 5 observations. Okay, all right, so we have observation till 255, and then we are predicting for the next 5 observations. uh, it Okay, what we can do is that for prediction purpose maybe we can use the real model. Okay, and then because it is giving the difference values, okay, which is what we don't want. We want the prices values, right? So we are using prices, and then the order is 111, because when you use a difference operator, then the predicted values are also in the difference operator, and then you have to, you know it's difficult to interpret, right? So better we estimate in this way and then use the prediction. Alright, so you can see the actual values. Of course there is a difference, the difference values are also there, but the actual forecast values from the last 5 observations, or the forecast observations using the ARIMA 111, are the following. Okay, so these 5 values are the forecast values for the next 5 periods, right? And you're fitting the data with ARIMA 111 with the first difference, first air terms, or first lag of air terms, and first MA term, or one MA term. So that's how we can use ARIMA model in R to fit a non-stationary data. We have already seen how to fit a stationary data. We also learned that prices normally are non-stationary. Return series is mostly stationary because it is already differenced, right? When you calculate return, you actually take a difference of the consecutive prices and divide it by some prices, and then you calculate the return percentage. That's already different, hence it's likely to be more stationary. Thank you.